In my last video, I built this little module here, the 555 timer module in a stable mode, and I promised to describe to you in this video how I actually designed it to fit on such a small piece of stripboard. So I'm going to go through the design process for making a very compact stripboard based layout for a circuit. And this is a unique method that I developed over 30 years ago and taught to many students over the years. So I'm going to show you it today. But first of all, I need to redraw the circuit which we started with, which was way back here. So this was the circuit that we started with, and that's what this little circuit board is. Where's it gone? So this circuit here is this circuit here. And I'm going to redraw this circuit because there's a couple of little extra features that I need to include because they are quite important. And that is the actual wiper arm of the variable resistor here and here for these two variable resistors. So we have to take those extra legs into account. So I need to redraw this circuit. So I'm going to do that now. Okay, so this is the circuit drawn out, or rather redrawn out. And all the components that are on this circuit are on this board. Now, the thing I need to show you now is the method by which this circuit layout, how this was designed. So I'm going to grab this pen and I'm going to do something now which you've probably never seen before, and it's a method that I call node analysis. And that is, you label all the nodes that are on this circuit with a number, a unique number. So I'm going to label these now, and I'll explain this as I go along. So the positive rail here is the easiest one to recognize here, and it connects to this LED here, to the 555 chip with a couple of lines here for pins 8 and 4, and it connects to this resistor here, RA1. So I'm going to call this node number 1. Okay, so that's node number 1. Node number 2, I'm going to call the negative rail. So this is node number 2. And node number 3, I'm going to decide is this output line here. That's nice and convenient because it matches up with the pin 3 of the IC there. So that's node number 3. Node number 4 I'm going to declare is this one here, which connects pins 2 and 6, the cathode of this diode here, this end of this variable resistor here, and this capacitor here. So that's going to be node 4. And node 5 is going to be this one here, this line here that connects these two anodes of these two diodes with these two resistors here. So that's going to be node 5. And now it's a case of numbering up the remaining nodes. So I'm going to call this one here node 6. Yeah. Node 7 here. that's the junction of the one of the legs of the variable resistor RB2 with the fixed resistor RB1. Node 8 is the cathode of diode D2 to pin 7. Node 9 is going to be this one here. This is the cathode of this red LED with this resistor here. 9, we'll call that 9. There we are. Number 10 is this one over here. We'll call that number 10. And now we can see that there are 3 unused legs, and they are here, the unused end of the variable resistor, the skeleton variable resistor, it's unused, and the other end of this skeleton resistor here, the unused leg there, is also needs to be marked up. So let's do that. So I'll call this one 11. That's 11. I'll call this one 12 here. And pin 5 I'm not using on the 555, and I'm going to call that number 13 there. Right, there we go. So even the unused legs are labelled up with a node number. Okay, so this is my node analysis. Okay, so the reason you do this is because this tells you precisely how many connections there are in the circuit. Even the unused connections, you have to declare them. Now that I know what these connections are, I can start working out how many tracks and how many connections I need on this piece of stripboard. And you can see here I had 10 tracks here, I had 10 strips. So that would make 10 connections, but the IC, the principal player in this is the IC. I have to break the connections on the underside. So that's going to give me 4 nodes on one side of it and 4 nodes on the other side of those breaks. So that's going to double the 4 connections there. So that's going to give me 14 connections by default, but I need 13. So that in theory gives me more than I need. However, I also need to make some connections from one side of the chip to the other side of the chip. And I also want to keep this space as minimal as possible. So now we're talking about some design considerations that need to take place when I'm doing my layout. And I'm going to explain what happened there. But in theory, we've worked out how many connections we need. And that is, we need 13 connections. So this is a very useful diagram to have. So now the question is, how do we get from this to this? Well, I'm going to take you through all the steps that I went through with complete frankness. So I started out with my first iteration of this layout. And I drew the 10 copper strips on this piece of paper, and I laid out my chip in the middle, and then I started working out what the node numbers are. And principally, you start with the component with the most legs on it, which is the chip. And you work out what the node numbers are. So we can see here, the 555 has got node 1, node 3, node 13, node 2, node 4, and node 8. So they all translate onto this layout here. So there's node 1, there's node 3. You see that? Yeah. and there is node 8 there, and there is node 4 here and here. Now, how did I get node 4 to get from this side to this side? Well, if you follow it up here, you can see I made a connection up to another track here. So I declared that track also as node 4. So I've got 3 places where node 4 exists. It exists on pin 6 on that track there with pin 6. And it exists on this track here, which is above the chip on an empty track, which I also declared as node 4. And then I took a wire down to pin 2, which is also node 4. So this brings us to some design considerations that we need to think about. So in my first iteration in the design of this layout was I wanted to have the minimal number of connections, of course, but I also wanted to have some symmetry in the circuit. And I also wanted to have the tracks that need to go from one side of the chip to the other side of the chip to be made only with vertical links. So there's no, I could have, for example, for node 4, which connects pin 6 to pin 2, I could have easily snuck a wire on the underside to connect directly from pin 2 to pin 6 and just bridged it across like that. You see a lot of other YouTube videos where they do this, and it's, of course, it's legitimate, it's perfectly fine to do that, but it's ugly. It involves being poor in your layout, and that's why you see a lot of the dead bug circuits that you see on YouTube taking this shortcut. They build things in midair and they connect wires all over the place, higgledy-piggledy. There's no design consideration there whatsoever. I wanted to keep the circuit very neat with all the link connections being made vertically. So that was one of my design criteria. Secondly, all the components are in the vertical plane. So all the components are vertically aligned. The only exceptions to that are the 2 variable resistors, because they don't have that kind of structure. So they had to be laid out in a slightly different way, which was horizontally. But having those design considerations in mind, whilst also trying to keep the circuit as small as possible, was one of my main design criteria. The next design criteria that I had in mind was I wanted to keep the circuit symmetrical. So that meant having the 2 variable resistors, these 2 preset variable resistors, either side of the chip, but I also wanted to have the LEDs either side of the chip. And so that's how this early iteration of this circuit looked like this. I had the red LED on the right hand side and the green LED on the left hand side. And you're going to see later on why this changed. You can see here I also made a mistake here. But the important thing you can see here is that the node numbers from the circuit diagram here translate to the circuit layout on the strip board. All the numbers were taken out. So you can see here pin 8 of the IC, pin 8 is node number 1. So there's pin 8 and that's node number 1. So that track is node number 1. But I also took it down to this spare track down here, and I declared this also as node number 1, making it from one side of the chip to the other. So I could get around that track break there. So it comes down here, goes to here, and then goes back up to make it to pin 4 of the chip, which is also node 1 here. And so that is also node 1. So we've got 2 node 1s connected together here, adjacent to each other, and they're made by that short link there. But this gives me multiple opportunities for my layout. So you can see here RA1, and here's RA1 here, which connects to node 1. So that's here on the right hand side, and there it is connected to node 1. And then the red LED anode also connects to node 1. So the anode, one side of the LED, connects to node 1, and there it is there. The anode of LED 1, the red LED, is there. It's also connected to node 1. So you can see here, this now just fills out like a jigsaw puzzle. So that was the initial layout. And now I want to show you the second iteration. And before I do that, from this layout, I hadn't figured out what the final size of the piece of board was going to be. I hadn't figured out how big it was going to be. But if you count them, you can see here that we have 1, 2, 3, 4, 5, 6, 7, 8. This is 0.4, so that would be 9, 10, 11, 12, 13, 14, 15. And then on the other side, 16, 17, 18, 19, 20. And then this would have been 21, 22, 23, 24. So this would have been 24 holes across, which would have been 2.4 inches. So it's quite a bit bigger than I expected it to be, or than I wanted it to be. But you're going to see now in the next iteration. Oh, here we go. This is the second iteration. It's in the book. And you can see here, let me just put this out again so you can see how we get from, can we see that? Let me just bring this down a bit. Okay, just do this like this. Okay. So this is the second iteration of the layout. Now what happened was I'd made this mistake here, so it inevitably meant I was going to have to redraw this manually. And with this being a relatively complicated circuit, I thought I'm going to need to redraw this anyway. And I wasn't quite happy with some items of the layout here. And I thought, right, well, okay, I will move this variable resistor inwards. And in moving it inwards, it's going to give me an opportunity to make the circuit a little bit more symmetrical. So you can see here that I got the variable resistors and the LEDs lined up in the vertical plane here. But I also wanted to reduce the number of holes going across. And that would entail moving some items. And I wondered if I could move some of the components. So for example, if I was going to move this variable resistor inwards, I could swap it with this wire link that's going to be here and move that outwards. And I will also move the capacitor inwards as well. And in moving that wire outwards, I would also move this resistor here. So that would make room for both the variable resistor and the capacitor, which you can see repositioned over here. So you can see this link moved outwards and is now over here. And quite conveniently, with it being moved over here, it lines up with this resistor here. So it's going to take up less space. And if I could repeat that trick with this link here later on, then it would mean I'd need one less hole in the vertical plane here. So that was what was happening on the left-hand side. And on the right-hand side, I had a similar idea. I wanted to move some of these items here. So I wanted to move this wire and I wanted to move, let me see now, which one is it? It's this wire here, because I wanted to bring this variable resistor in another hole. So that meant I was actually able to reduce the number of holes required from 24 down to 22. So the other thing I moved was RA1 to be in line with the wiper of RA2. So it moved in by 1. And so all of these moved in by 1. And that reduced the number of holes. That reduced the number of holes from 24 across to 22 across. So I've got it down to 2.2 inches now by 11 tracks. But this was not the end of it. So I thought I could go one step further. And so what happened next was I thought, well, now you've got some other design considerations you need to take into account. Are you optimizing for symmetry or for space? And so I decided there was more to be gained by me optimizing for space. And so what I actually did was I swapped, let me just get this one out of the way, first iteration out of the way. I swapped this wire and made it line up with being underneath RA2, and also this diode here, D2, I moved to be under RA2, so that would save me one track. And I swapped this wire and I moved it over to here so that it straddled this track break here. So that would save me another track. That would save me another hole. So this would all collapse down by another 1/10 of an inch. And similarly on the left hand side, I moved in RB2, so it was much more in line with the chip. And I swapped this link here and moved it over to here in between these two 1K resistors, and I put a track break just about there, and that meant that I could move this LED right to the end, and then I could move this LED all the way to be in line with this resistor, but with this resistor up one. So there's only 2 items on that track there, node 9. And that meant I could get rid of node 10 altogether and have node 9 on this side and node 10 on this side. And I'm going to show you that in the final iteration of this circuit layout, which I did on the computer as a paint diagram. So I only used Microsoft Paint and it worked out perfectly fine. But what it meant was I got this circuit down from, you can see here, drawn accurately, 22 holes by 11 rows down to 18 holes by 10 rows. And you can see how small it is. It's smaller than the actual layout here that I previously estimated. That was this version here was going to be 22 by 11, and I got it down to 18 by 10. You can see it that way around perhaps. So that's how you do this layout. Now the other thing that I need to mention was going back to this layout node analysis here, the circuit diagram node analysis, and I had to redraw the 2 variable resistors, the 2 preset variable resistors, and I labelled the unused legs with node numbers and pin 5 of the 555 with a node number, because I had to make sure that nothing else connects to them. So you can see here, pin 5, nothing else connects to it. But the unused legs of the two variable resistors, that's this leg here and this leg here, I had to make sure that I put a track break between them, because if I didn't put that track break between them, it would mean that these two legs were connected together, and that would give us a completely different circuit, and that would not be good, because then it would change the function of the circuit. And the last bit is the other track break was this track break here, which was breaking the connection between the RB2's wiper leg and RA2's wiper leg. So this is node 7 and this is node 5, therefore this needed to be a track break here. So that's why those track breaks are there. So next we're going to look at the final iteration, which leads us to the final layout that you see here. And you're going to see it's very colourful and very interesting to look at. And so we come to the final iteration of this circuit layout. And you can see here the nice paint diagram that I did on the computer, showing the full layout of all the components with all the modifications that I mentioned just a moment ago. And you can see here down the left hand side and the right hand side, you can see all the node analysis numbers, and you can see between the tracks there are 8 white track breaks, which you can see on the topmost track, which starts with node 11 on the left hand side, and then just after RB2 you can see there's a white track break, and then on the right hand side you can see it's node number 12. So that's how the track breaks show you the separate nodes either side of the track break. And you can see here the concentration of the red and green LEDs in the bottom left hand side of the circuit board. And that's pretty much it, really. So this is how you lay out very efficiently electronic circuits with a manual method to get a good layout and a very efficiently laid out circuit. Thanks for watching, and I will see you in the next one.